So I'm going to show you to use the Milnor-Thurston kneading theory to study the dynamical behavior of iterated functions of a compact interval. Like say f here is some kind of function mapping from the closed interval 0 to 1 back into that same interval. So these are always going to be endomorphisms of some compact interval, and we're going to require that they be piecewise continuous. You can study discontinuous functions, but those discontinuities must be removable. So in fact, if you have something like absolute value of 1 over x for your function, that's not going to be treatable, firstly because it's not mapping onto a compact domain. It'll map onto something like 0 open to infinity open. So they have to be removable discontinuities, which you get for free by saying the domain and the codomain are compact and the function's piecewise continuous. So John Milnor, William Thurston are two super famous American topologists from the mid-1900s. They took an interest in dynamical systems and did a lot of foundational work there. And they came out with this paper that showed, so dynamical systems are some kind of state space where the state of some physical or biological or something system can be represented by a point, and that point is going to move around in time. So you got some kind of evolution law that dictates what the behavior of the system is. So in our case here, our state space is 0 to 1 closed, the interval that's the domain of our function, and the evolution operator is just applying f to a point in this interval. So you can repeatedly apply the function f to a particular point and watch its iterates move around in the state space, and we call that sequence of iterates the itinerary of that point. So the simplest dynamical system that most people consider is this kind, just a iterated function of a one-dimensional interval, right? There are other simpler ones, like if your state space were discrete. So if you just took, say, 3 points and imagine you define some kind of evolution operator on those 3 points. So you do an iteration of some permutation or something on those 3 points, then that would be a dynamical system, which is simpler than this, but those are mostly uninteresting. So this is kind of the first thing that you study when you begin studying dynamical systems. So Milnor and Thurston gave us a way to grapple with this. They kind of gave us a complete picture. So they released this monograph, and it didn't get published. It was just this pamphlet, sort of, and they passed it around at Princeton and sent it to professors everywhere else, and everybody kind of knew the theory, and it wasn't published till much later. But I'm going to walk through the procedures of that paper here. So the idea is you'd like to characterize all of the behavior available given a specification of some interval that you have as your state space and some iterated function that you'd like to be your evolution operator for your dynamical system. So I'll walk through the procedures in detail, but it's kind of going to go from the top to bottom here. You compute this for your function and this, and then, well, you do this as well, and then you look at particular points in your domain. So those points are these turning points where you have like a local maximum or a local minimum, or you have a discontinuity in the function, and those become your turning points. Generically, when you have a discontinuous map, these are just critical points or discontinuities. And then the turning points partition the interval into laps. So if I chop the interval at different points, it will partition that interval into pieces, which we call laps. And the interval, the function is going to be monotone, increasing or decreasing on each of those laps. And if it's increasing, then you assign a lap orientation of +1, and if it's decreasing, you assign a lap orientation of -1. Very simple. And then you'll consider the itineraries of points very close to those turning points, And from that, you'll construct these things called Kneading coordinates, which are just sequences of symbols basically representing the cumulative signed laps that you traverse as you let those turning points be iterated around in the state space. So they'll jump around everywhere, and where they go, you just record that down, and you keep track of what orientations you've seen so far in terms of the laps that you hit. And then you construct from the Kneading coordinates a Kneading series, which is just a power series representation of the sequence, which is the Kneading coordinate. And the Kneading increments then track how the endpoints of the laps move as you iterate the laps around. So they have this capability of tracking discontinuities. So this is kind of where you handle discontinuous functions here. If you were only restricted to continuous functions, you would actually be able to come up with a Kneading theory that does not require you to specify these Kneading increments. And then you encode these Kneading increments through some kind of strange operation, which we'll see towards the end, in this Kneading matrix, which is a matrix made of entries which are power series with integer coefficients. Then you do something to make that matrix square, and then you take its determinant, and that gives you this Kneading determinant thing. And then once you've done that, you can compute the topological entropy of the dynamical system, which is that iterated function on your interval. And the topological entropy, if it's 0, tells you that there's no chaotic dynamics, so everything kind of converges eventually to some stable configuration, no matter where you started. Or if it's positive, it tells you that there's some points, at least, where if you iterate those points around, you'll have chaos forever. So they'll converge to some chaotic set where things will bounce around unpredictably. If you have a little bit of measurement error, then your predictions for where those points will go in the long run will diverge very quickly. So this gives you a way to characterize very easily, just using only the itineraries of these turning points, which, there's maybe 1, 2, 3 of them per function, whereas there's uncountably infinitely many points in the domain of the function you might want to characterize. Just those finitely many turning points will give you all the dynamical information about the function as a dynamical system. And then in a future video, if I get around to making it, we'll talk about how to go a little bit further than this and come up with other invariants besides the topological entropy. But we're going to reuse everything up to Kneading determinant. And those other invariants will allow you to do things like characterize how many periodic orbits of a certain period there are, characterize how hard it is to get particular periodic orbits of a certain period, which ones precede others, which ones make it so that others have to exist. Like how there's if I have a period 3 orbit, I'll be guaranteed chaos no matter what. So there are a lot of rich theories that go with this that kind of came after, and maybe a little bit before, very briefly before, that tie into this and give you a complete picture of one-dimensional dynamics with discrete time operators. All right, so let's go ahead. Kneading theory lets you understand the behavior of piecewise continuous functions applied repeatedly to points in the domain. So here I've got this continuous function, which is a cubic. All right, so maybe this takes the form of f of x equals ax cubed plus bx squared plus cx plus d, where a, b, c, d are all real coefficients. And I would like to understand what happens if I pick some point in the domain, like let's say right here, and I check where it maps to. So it maps to this y value, so to speak, which I can then draw over here on the y-axis. And then I can think about what happens if I apply the function again. So I can look at where this is on the y-axis. So let's go ahead and label these axes. So they start at 0 and end at 1. In general, that's going to be the convention we'll use. These functions have domain and codomain of the closed interval 0 to 1. So I look at this point where the original point mapped to, and then I draw it on the x-axis. So it's somewhere closer to 1, so let's say somewhere around right here. Well, then I can look at what the second iterative of f does to this point. It firstly maps you to this point, and then that second application of f maps you to this value, which you can draw over here. Now, it's hard to be exact about this, right? So one trick I can use to help me evaluate repeated applications of f is to draw this bisectrix, or this identity line, y equals x. And instead of going to the y-axis then, once I hit the function graph going vertically from some point in the domain, the image is going to be on this bisectrix, so I can just draw horizontally till I reach this line. And then I can go vertically again. So I kind of missed it a little bit. I should have been right here, actually. And then I go horizontally yet again. And it turns out this is approximately a period 2 orbit. So I'll just go back and forth between these 2 points, here and here, over and over. So I would like to understand all the different kinds of orbits or itineraries of different points in the domain. So I could pick a different point to start at, and I could get some kind of completely different behavior. Like maybe it just converges to a single fixed point, and just kind of slows down and ends up at one place and stays there forever. Or maybe orbits generically just jump around everywhere, and they kind of chaotically never settle down or anything. You just can't predict what they do long term. They just kind of all get mixed together. That's a possibility. So it turns out that instead of evaluating every point infinitely many times to see where it goes, I can just look at a couple of critical points in the domain and evaluate those and see what their itineraries are, and that will let me characterize all of the dynamics in the system, so every orbit, or at least all but, say, finitely many, so to speak. So it turns out that the orbits that I'm interested in, the itineraries I'm interested in, are precisely those of the critical points, or turning points of the function. So there are 2 for this cubic. There's one here, and one here. Local maximum, local minimum. If it were piecewise continuous, then I would look at the left-hand side and the right-hand side of every discontinuity, as well as the local maxima and local minima. But in this case, we don't have to worry about that. So I've got 2 turning points, C1, which we say is this point, and then we call this one C2. I'm going to fill out the rest of this data. So the critical points split up the domain into laps, or piecewise monotone intervals. The first lap is between 0 and C1 here. So we call that one I1. I is just short for interval. Okay. Then we have I2, which is between C1 and C2. And then I3, which is between C2 and 1. Now each of these monotone intervals has an orientation, either it's increasing or it's decreasing. So I1 is increasing. So the way I write that here for lap orientations is epsilon 1, which corresponds to I1, is, well, it's positive because I1's increasing. Or at least the function is increasing on I1. Epsilon 2 corresponds to lap 2, so that's going to be decreasing, so negative 1. And lap 3 is increasing. So we get positive 1 there. Now I need to know what the itineraries of these critical points are. And the way I write that is as follows. I don't actually care what the itineraries are of the critical points. I want to know if I looked just to the left, very, very close to the left, epsilon close, so to speak. Not these epsilons, but some small delta distance, infinitesimal away to the left, I would have a point we call C1 minus. And to the right, I would have a point we call C1 plus. And you can just let those get closer and closer as needed to do whatever later results we need. Here I've got C2 minus, on the left side, and on the right side I've got C2 plus. And I want the itineraries of these points. So the way I write that is an itinerary is written k of some point. So k of C1 minus is, and we're just going to record the lapse that this point hits as we repeatedly apply f. So the very first thing that happens is C1 minus lies in lap 1, I1. So we go ahead and record that. That's the 0th iterative f when you haven't applied it at all yet. Now the first iterative f is going to take you to, well, let's see. So let's just check where the critical point C1 itself goes. So that goes horizontally to the bisectrix and lands over here somewhere in I3. And because C1 is arbitrarily close to C1 minus, C1 minus is going to go also in I3. And then it's going to map over here back into, it looks like I1. And that point is going to map also, it seems like, into I3. And it looks like it's getting, let's see, it went a little bit further out this time, so over here. So I1. And it seems like it kind of just alternates back and forth. And it stays going between I1 and I3 forever. Okay? Never quite hits one of the other critical points like C2 or C1. On the other hand, C1 plus has the same itinerary, except the very first point in the itinerary, C1 plus itself, lies in I2. So the 0th iterate of f is instead going to be in I2 instead of I1. And then the rest is going to be the same, because it should follow C1 very closely. Both of these should. So it's I3, I1, I3, I1, I3, I1, I3, and so on. All right, we've got two more. So C2 minus, well, that starts in I2 because it's just on the left of C2. Then it maps over to I1, and it seems like it hits the same orbit that the itinerary of C1 had, so it's just going to alternate between I1 and I3 forever. So I1, I3, I1, I3, and so on. Similarly, C2 plus is going to start in I3 because it's on the right side of C2. And it's going to map to I1, and then that's going to map to I3, just that point. I1, I3, and so on. So those are the critical itineraries of this map. Now we want to know the Kneading coordinates of the critical itineraries, or of the points just off from the critical points, C1 minus, C1 plus, and so on. And the way you get this is, well, these are written like so. They're also sequences. So if I have a point x in the domain, the Kneading coordinate for that point is going to be a sequence with theta 0 of x, theta 1 of x, theta 2 of x, and so on forever. And these thetas with the subscript, theta I of x, so I corresponds to a particular iterate of the function. So the 0th one is after 0 iterates, this is 1 iterate, just like we did here with the itineraries. That's going to be the lap, so we're actually going to write in the lap here that corresponds to that iterate of x. corresponding iterative x. So say if I wanted theta 0, I would look at, for C1 minus, I would look at I1 here, because that's the 0th iterate of the function. It's the lap that lands in. So K1 of C1 minus would be 1, because that's the index of the lap that you land in after 0 iterates of C1 minus. That's what this is. So it's the lap you land in on the k-ith, on the ith iterate, times the product, let's see, yes, the product over j from 0 to I minus 1 of all of the orientations of the laps that you hit on the way there. So what this is going to do functionally for us is we're just going to keep track of whether we hit an orientation reversing branch, like this lap 2, or orientation reversing lap like lap 2, which has epsilon 2 being -1. And those negative ones are going to accumulate here. And we're just going to flip the sign of the laps that we write down every time. So for C1 minus, the Kneading coordinate is going to be the same as the itinerary in terms of which lap we write. So it's I1, but is I1 orientation reversing or preserving? So it is increasing, and epsilon 1 is 1, so that is going to not have a sign change, so it will just be I1. I3 next, well, epsilon 3 is 1, so we don't reverse the sign. And this keeps on with I1, I3, and so on. Theta of C1 plus, on the other hand, does actually see a sign change at the first one because it hits this decreasing lap with epsilon 2 equals -1. So we write negative I2. And then I3, but that's negative because we have to accumulate our sign changes by this product. And the rest of them are orientation preserving, so we keep the negative the whole time. So that's that Kneading coordinate. For the others, C2 minus starts at I2, which is decreasing. The rest are increasing. And then theta C2 plus, all these are orientation preserving. The laps are increasing, so we just write out exactly as the itinerary was. Okay, so those are the Kneading coordinates. Now that we have the Kneading coordinates, we'd like to compute what are called the Kneading series. And I'd like to note something real quick. I'm going to make an algebraic object called M. And this is going to be a free Z module, which has, if it's free, it has a basis. So that basis is the set of laps of our function f. So that's I1, I2, and I3. Now to write out exactly what that means, if you haven't played with Z modules before, it means that M can be written as a direct sum of integers times I1, direct sum, integers times I2, direct sum, integers times I3. So this is some kind of algebraic set or object, and it's a set, and it has elements, namely it has 0 as an element. Another element might be I1 itself, but I can also write negative I1. That's another element because it's an integer times I1, -1 times I1. On the other hand, I can take arbitrary linear combinations of I1, I2, I3 with coefficients being integers. So an arbitrary element of M looks like, let's say, A I1 plus B I2 plus C I3, where A, B, and C are integers. And this is only equal to some other linear combination if these coefficients are exactly the same for both linear combinations. So there's not some way to add some more of I2 and get some multiple of I1. You know, they don't. They're independent. It actually is a basis in the sense of linear algebra. It's like a 3D vector space where your basis vectors are I1, I2, I3, but you just aren't working over a field, so your scalars are coming from the ring of integers instead of a field, so you have to call that a module. So the entries in these Kneading coordinates, I3, negative I2, negative I1, positive I1, so on, are elements of M. They're in this module. And the Kneading series is going to be written, and we'll have 4 of those. So theta, again, we're going to overload that notation, and we're going to have 1 for each of the Kneading coordinates that we cared about, 2 for each critical point. So C1 minus, and then we're going to put another parameter here, T. And this is going to be a power series with coefficients being precisely the entries of the Kneading coordinate corresponding to that. So it's going to be I1, and then plus I3 times T, where T is just some indeterminate. You could use another letter if you like, but it doesn't matter. And then plus I1, the next entry, T squared, plus I3, T cubed, plus, and so on. This goes on forever with that Kneading coordinate. On the other hand, the Kneading series for C1 plus is negative I2 minus I3T minus I1 T squared minus I3 T squared, cubed, and so on. For C2 minus, you get a Kneading series which is negative I2 minus I1 T minus I3 T squared minus I1 T cubed plus ... And for C2 plus, you get I3 plus I1T plus I3T squared plus I1T cubed plus, and so on. So note, if you have some point in the domain X, then the Kneading series corresponding to that point is going to be an element of the power series ring with coefficients in this free Z module with basis I1, I2, I3. And the indeterminate for that power series ring is T. Okay, that's what kind of object this is. Now I'd like to recall that I did not require for the function that we're taking iterates of to be continuous. I only needed that it be piecewise continuous, so it could have discontinuities, particularly removable discontinuities. In this example, you've got the same kind of setup. You've got 2 turning points. And you've got 3 laps, I1, I2, and I3. And each one has the same sign as it did before. You've got increasing, then decreasing, then increasing. So in this example, I need some way to study the, I need some way to represent the fact that the Kneading sequences, or the Kneading series, for each critical point, namely there are 2, one on the left and one on the right, I need some way to represent that they actually are different other than the first element. Because if we had continuity, then you would just have the first entry in the Kneading coordinate different for each of the left and right sides of a critical point. But in this case, the two sides may go to entirely different places, right? So this might map, let's say I drew my bisectrix here loosely. This might map to here, then here, which is I3, and then here, and then here, I2, and maybe this just converges or something. Or maybe it goes to a period 2 orbit. On the other hand, this one would go here, and then here, maybe just misses to the left there, and then shoots over here, so you actually hit I1. And so on. So the left and right sides can vastly differ. So you actually need some way of representing the difference across the whole Kneading series, or the Kneading coordinate for each side of the critical point. We need some way of representing the fact that the itineraries are totally different. So the way you do that is, once you've got your Kneading series written out, I've got 2 for each critical point. So 2 for C1, 2 for C2. And I come up with this thing called Kneading increments. And the way Kneading increments work is as follows. You write nu, the Greek letter nu, m. So m corresponds to a particular critical point. So m can range from 1 to 2. And this is going to be a power series. And it's going to be, again, in the power series over m, that free module. And it's going to be equal to the left Kneading series, the right Kneading series for the mth turning point, minus the left one. So it's just the difference in the Kneading series of the 2 sides of the critical point. So we have 2 of these. So nu 1, well, it's going to be firstly the right side, so C1 plus, so it's going to be negative I2, and then minus the corresponding term in the Kneading series for the left side, so minus I1. So negative I2 minus I1, and then you look at the first degree terms. So that's going to be negative I3 minus positive I3. So negative I3 plus I3, I'm just factoring out a negative t. Here, it's going to be negative I1 minus I1. And in general, it's going to be 2 times whatever if you have continuity at that critical point, because the iterates, the same iterate is going to land in the same lap, but it's going to have reversed orientation in one of them. So it's going to be minus 2 I1 T2 minus 2 I3 T3, minus, and so on. On the other hand, nu 2 T is going to be the right one, so I3 minus negative I2, so I'll just write I2 plus I3, plus I1 T minus negative I1 T, so plus 2 I1 T plus 2 I3 T squared, plus 2 I1 T cubed, plus, and so on. So those are my 2 Kneading increments, and I could simplify this one a little more if I wanted, but it's obvious how it's going to simplify, so I won't write it. Alright, I did decide to write it. It simplifies a little bit. So nu 1t, you have your constants, which don't have t in them, here. So it's negative I1 plus I2. And then you've got minus 2 I3 for the next coefficient, and then minus 2 I1, minus 2 I3, so on. And it just repeats negative 2 I1 and negative 2 I3 repeatedly. And then for nu 2, you've got your constants, which are just the 2 laps that are adjacent to the second critical point. And then you've got 2 copies of I1 for the next iterate, and then 2 copies of I3, I1, I3, so on. So they're very simple. And in general, it's going to look that way for continuous critical points, points where the function is continuous at the critical point. So here comes the kind of complicated bit. It's a little bit tedious to write out or to actually compute, but that is the Kneading matrix. Okay, so this is going to be written n of t, and it's going to be an element of, it's going to be a matrix actually, as it says on the 10, and the entries in that matrix are going to be power series with coefficients being integers. Okay, so it'll be a matrix, and at every component or every entry of that matrix, it's going to have some kind of integral power series. Okay, and the size of that matrix is L minus 1 times L. So L minus 1 rows and L many columns, and L is just the number of laps, which in our case is 3. So the way you actually compute this matrix is by trying to satisfy this condition. For the mth Kneading increment, nu m, you should be able to write that nu m as a sum, or a series actually. N is going to be the summation index, and it goes from 1 to L, which is the number of laps, and you will have, let me scratch that out actually, mn, the mth row in the nth column of the Kneading matrix, should be the coefficient of the nth lap in the power series here. Now this is a little bit weird because this doesn't strictly look like a power series, right? But recall, the entries of the matrix, which are specified by picking a particular row and column of the matrix, the mth row and the nth column in this case, are going to actually be power series with coefficients being integers. So each term in this sum is going to be itself a power series where in is the only lap that you see. You just see different multiples of it in that term. So we can compute this. Namely, let's see, what should I do? Maybe to be explicit, I can write out nu 1 and nu 2 this way. So nu 1 is going to go from n equals 1 to 3, because we have L being 3 in our case. The mth, so m is 1 in our case. So the first row and the nth column in the matrix should correspond to the coefficients of in, whatever n is, from 1 to 3. And likewise, nu 2 is the sum from n equals 1 to 3, where you're just looking at the second row of the Kneading matrix to get your coefficients for in. Okay. So let's build this. It should be a 2 by 3 matrix. So it needs to be 2 rows and 3 columns, but each one's a power series, so I need to leave some space here. Okay, so I should have 1, 2, 3, 4, 5, 6 entries. So the first one, well, the first row is going to correspond to nu 1, right? So to figure out what the first entry in the first row is, I need to look at n being 1. So I need to look at nu 1, and then furthermore I need to figure out where does I1 occur in there. Well, just take out the bits of this Kneading increment where I1 appears and look at the coefficients. So for the constant term, you only have I1 appearing once, and it's negative 1. So it's negative 1. Here it doesn't occur, so you don't have a linear term. You do have a quadratic term, though. You have minus 2 t squared. You do not have it in the cubic term. You have it in the quartic term, where it will again be minus 2 t to the 4th this time. And it just alternates back and forth between I1 and I3 in the Kneading increment, so you have all the even power terms. Okay, so that's the first one. I realized I should have left some more space. But for the second, I only have I2 in this first place. We never hit I2 otherwise. And it gets a coefficient of -1. So it's quite simple. On the other hand, I3 gets, well, it's not in the constant term, but it is in the linear and the cubic and all the other odd power terms. So it's going to be -2t minus 2t cubed minus 2t to the 5th minus so on. So that's the first row of the Kneading matrix. Now the second one, you just look at new 2. So I1 occurs at the linear term, the cubic term, and so on. So it's 2t plus 2t cubed plus 2t to the 5th, and so on. I2 only occurs in the first term, the constant term, and it has a coefficient of 1 there. I'm staggering these because this one's probably going to be a little bit bigger. I3 occurs in the constant term, so 1, and it also occurs in the even-powered terms, so plus 2 t squared plus 2 t to the 4th plus 2 t to the 6th, and so on. Okay. So I've collected everything here and written it a little more neatly. This is the Kneading matrix. So it has 6 power series entries. These are very simple. These are all fairly simple, actually. And it's helpful to know that if you have an integral power series like these entries, you can usually rewrite it using the geometric series formula. So the geometric series formula is this. If you've got a power series with 1 for every coefficient, then you can rewrite this using this nice formula. So it's just this rational function, 1/1 minus x. So I can use this to actually simplify all these and write them out and get everything, instead of having to write an ellipsis and just saying that it goes on like this forever. I can actually get it to be an exact description of what those power series are. So let's try rewriting the Kneading matrix a little bit using this. Okay. So I'm going to use a pen to do a little scratch work here. Let's call this f of x. Maybe I should be using t. It doesn't really matter. So this is a polynomial or a power series. So I can plug in any number or symbolic expression and for x, and it will fill this out. And whatever I did to x should also appear here. And so I can just say that if I can plug in something that turns this into a power series up here, then I should be able to re-express it as a rational function. So the first one, it looks like it looks like I can't get these 2's to come out of this thing, because if I put a 2 in here, then when I square x, the 2 is going to get squared as well. When I take the cube of x, it's going to square that as well. So that's not exactly going to work. I need to do some kind of trick. So let's say I write -1 minus 2t squared minus 2t to the 4th minus 2t to the 6th, and so on, which is that first entry in the matrix. I could actually factor out a 2, a -2 from the whole thing. So this is equal to -2 times 1/2 plus t squared plus t to the 4th plus t to the 6th, and so on. Okay. Well, it would be nice if I could just get a 1 here so that it looks kind of like this guy. I know the powers are different, but that's all right. So I might add a 1/2, so this becomes 1, and then subtract the 1/2 outside. So let's do that. So let's go ahead and subtract that 1/2, and then we've got plus 1 to accommodate for this 1/2, plus t squared plus t to the 4th plus t to the 6th, and so on. Now this -2 Yeah, -2 and -1/2 become just +1. So I can just go ahead and multiply these and then distribute this -2 to the rest. And I get 1 minus 2, and I'll leave all this except the 1/2 factored out. So it's going to be 1 plus t squared plus t to the 4th, and so on. And remember, we've got, I shouldn't be writing f here. This should maybe be like s for series, we'll say. I could use g, whatever, doesn't matter. But this now is equal to 1 minus 2s of t squared. Because I get this in the parentheses if I plug in t squared everywhere there's an x here. So, because s of x is equal to 1 over 1 minus x, this can be rewritten as 1 minus 2 over 1 minus t squared. I just replace the x with t squared here, and then multiply by that 2 that's left over as a coefficient. So it turns out that the first entry is, in fact, 1 minus 2 over 1 minus t squared. Okay. The second entry is -1 again. Oh. Okay. Can I do anything else here? Well, it turns out that this is just the negation of that, so I should be able to just negate it. And get, well, this one's 1, of course. So, yeah, just double checking, that is the negation of that one. I didn't write it. This one's the negation of this. So I should be able to, if I get a formula that this is equal to, namely this, then I should be able to negate whatever that formula is to get a formula for this. So that's going to be 2 over 1 minus t squared minus 1. Okay. Now we need one for this and for this, and they're negations of each other, so really we only have to find one of them. So let's see. I'm just going to work with the positive one because it's a little simpler to deal with. I can factor out a 2t from the whole thing. I get 1 plus t squared plus t, what is that, t to the 4th, plus t to the 6th, and so on. Well, again, this is s of t squared. Which is equal to 2t over 1 minus t squared, using this. And so that's the expression for this bottom left entry. So this one's going to be the negation of that, -2t over 1 minus t squared. Or I could write t squared minus 1 in the denominator, but it doesn't matter. So this is the Kneading matrix. All rational functions, all power series, and very simple. You can write it in very compact form, and there's no ambiguity about what the pattern in the power series ought to be. So this is very nice. All right, so I've collected the Kneading matrix here. This is what we just found. And the next step, now that all the hard work's done, is I would like to compute the Kneading determinant. So the Kneading determinant is, so to speak, some kind of determinant of this Kneading matrix. But the trouble is that this matrix isn't square. It's always going to be a wide matrix with one extra column compared to the number of rows it has. And actually, the number of rows, or each row corresponds to a turning point, and each column corresponds to a lap. So, of course, it's going to have one more lap than it's going to have turning points because you're splitting up an interval, the domain 0 to 1. At each of the turning points to get one more lap than you have turning points. So that's why that always comes out wide. So we need to do something to this Kneading determinant to get, or to this Kneading matrix to get it to where we can take a determinant. So the idea is we compute what's called D1, which is delete the first column and compute the determinant of the rest of it. So we're going to ignore this from now on. This is not important. And it's kind of nice that actually these terms are what appears here as well, just negated. So we're not really losing any data. And in general, I believe this is going to be true in some sense. It's not that there are going to be negations over here or negations somewhere else, but at least the data that's encoded in those entries in the first column, those data are going to be presented elsewhere in the matrix anyway. It's redundant information. So we want to compute the determinant of this thing. So how do we do that? Well, pretty easy. Use your Laplace expansion, or just multiply across and then subtract the product of these two. So it's going to be this times -1. I'm just going to write 1 minus 2 over 1 minus t squared. Minus the product of these two. And so this minus will go away. Oops, that should be a minus. Or a plus, actually. 2t over 1 minus t squared. So does this simplify at all? Well, I could write 1 minus 2 over 1 minus t squared. And then I've got one copy of that, and then that's negative, and this one's positive with a t. So that's going to be 1 minus t. That cancels out with this by, what do you call it? Difference of squares. So I could, to be explicit, let's just write it out. 1 minus 2 times 1 minus t over, and then this is a product of 1 minus t and 1 plus t. So these cancel. I'm left with 1 minus 2 over 1 plus t. So that's the kneading determinant, or the d1 that we need to compute on the way to the kneading determinant. Now, to actually get the kneading determinant, d, I need to divide this d1 power series, or rational function, by 1 minus epsilon 1 of t, right, times t. Now, epsilon 1 was the orientation, or the sign of the first lap in our function, which, if you'll remember, was increasing because our function looked like this. So that first lap is increasing, so epsilon 1 is just positive 1. So it's going to be 1 minus t on the bottom. So this becomes 1 minus 2 over 1 plus t over 1 minus t. And I can simplify this, of course. I have to get a common denominator up here in the numerator. So I'm just going to make this 1 plus t over 1 plus t. 1 plus t, and then minus 2. And on the bottom I've got 1 minus t. And again, I can combine these two to get 1 minus t squared. And I can cancel, or I can do that subtraction to get t minus 1. So actually the numerator is going to cancel with this denominator here. So that's going to be, what, t minus 1. Which I'll write as negative 1 minus t. Over 1 minus t. This and this cancel, and I'm left with negative 1 over 1 plus t. So that is the kneading determinant for a map. Okay. Now, that is essentially everything that the kneading theory gives you as far as characterizing the complexity of your dynamical system, whether it's chaotic or not. I have one tool that comes from the kneading determinant I can use, which is called the topological entropy. And if you'll remember from the sort of review sheet at the beginning with all the formulas, the topological entropy is written h sub top. So h is common notation for entropy, and top short for topological, of the function f, which is the cubic that we had the graph of. That's going to be negative log, and you can choose the base here freely, of the absolute value of r, and this is going to be in general non-negative. It could be 0, it could be a positive number, it could be positive at infinity, but never negative. And so this whole quantity is, I know I've got the minus sign, but this r is going to be required to be less than 1. So what I mean by that is r is gotten from this. I want this to be true. The Kneading determinant is a power series, and it should have r as a root. Now, r, in fact, is going to be the smallest root. So if I look at the complex plane, let's see. So this is the real axis. This is the imaginary axis. 0 is here, and you can imagine that 1 is right here, I is here, -1 here, and -I here. Well, if I draw the unit circle, I'm assuming you probably, this isn't a circle very neatly drawn, but I'm assuming you probably know about how to take the modulus of a complex number. You can plug any complex number into this Kneading determinant, which is a power series, and evaluate what the Kneading determinant produces with that complex number plugged in. And you can get 0 for not only real inputs, but also imaginary or just general complex inputs. So you look at all the roots of this power series, and there may be arbitrarily many, there may be none, there may be finitely many, there might be infinitely many. And you, let's see, you find the one that's closest to the origin and call that r. So maybe you have some roots out here, way outside the unit disk. So this disk is where the modulus of some complex number z is equal to 1. And you don't care about things outside here. Now, your smallest root may not be in here. It may actually be this one, in which case this is r, and you can't get you can actually if r is greater than 1 in absolute value, or is equal to 1 in absolute value, then you say that the topological entropy is equal to 0. On the other hand, if you have a root that's inside the unit disk in the complex plane, then you look at its modulus, which is the distance from the origin. So this is r, and we're looking at the modulus of r. And if it's less than 1, which means it's in the unit disk on the interior, then this is the formula for the topological entropy. So you just look at the smallest root, take the modulus, and that's it. Now, no matter what I plug in here, I won't get 0, because I need a 0 in the numerator. So there is no root of this Kneading determinant. So it turns out that the, I should write, if absolute value of r is less than 1, otherwise the topological entropy is 0. And in our case, h top of f, well, there are no roots, and so vacuously, because r doesn't even exist, you have 0 here. Now, you could work with the Riemann sphere instead of the complex plane and just say that if you plug in the point at infinity for t, then you get 0, because you plug in a number that's arbitrarily infinitely large in the denominator, and this term goes to 0, this expression goes to 0 as you let the modulus get larger and larger for t. So it does have a root at infinity, but that's it. So the topological entropy for our cubic that we had drawn, let's see, let's draw the picture. Yeah. So this cubic has topological entropy 0, which means every orbit in the domain converges to some attracting set which is a periodic orbit. Now, it may be a disjoint union of a certain number of periodic orbits, but at least we do not have a chaotic set of points where if you plug in a point, then you just kind of wander around forever and you never settle down in some periodic orbit. So nothing is eventually periodic. Or excuse me, everything is eventually periodic because you don't have any chaotic set. So we've just shown, using the Kneading determinant and topological entropy, that there is no chaos in this system, in this function. So it looks to me like probably the only attractor in this is like a period 2 orbit or a period 4 or 8 or something. One result we have from the Sharkovsky theory is that if the topological entropy is 0, then your map is of type 2 to the k. So the only periodic orbits are all of period some power of 2. So everything has to converge to some power of 2 period orbit. There may be multiple different ones, but you know that everything must converge to that. I won't cover that in this video, but like the Sharkovsky theory I won't cover, but you can read about that. And the name of that is this, spelled this way, Sharkovsky. So he gives an ordering of the natural numbers, where you can order how hard it is to get different period orbits in these 1D maps. But yeah, this is the topological entropy, and it fully characterizes what kinds of sets occur in the domain as far as the dynamics are concerned. On the other hand, if we were to go further, which we won't in this video, there are a couple of things that you can use to characterize the dynamics a little more descriptively using the Kneading theory that we've just talked about. One is, if you'd like to know how many periodic orbits of a certain period there are, you can use what's called the Artin-Mazur zeta function. I may make a video about this. So Artin-Mazur zeta functions. What else is there? There's a couple of videos on YouTube about Ruel transfer functions and their relation to the Kneading theory, or transfer operators. We could also go over a proof of the Kneading theory, or in particular the topological entropy formula. The one depending on the smallest root of the Kneading determinant. That's the subject of much of the original paper by John Milnor and William Thurston. And let's see, I think there was something else I wanted to say. So the topological entropy here, when you take the logarithm, if I had had a chaotic set in my domain 0 to 1, I would have gotten some r with absolute or modulus less than 1, and I would end up taking this logarithm. Now, I can choose any base for the logarithm. So we'll call that units of entropy. And if I had chosen a base for the logarithm of 2, so this is log base b of absolute value of r minus log. If I had chosen b equal to 2, this would be the Shannon, or bits of entropy, the Shannon entropy. If I had chosen e for the base, Euler's number, this would be called nats of entropy. And there are a couple of others. I can't remember what it's called when you use 10. Let me look it up. Okay, so if you use base 10, these are called Hartleys or bands or dits. So the way they write that is hearts, bands, or dits, which means decimal digits. And I think those are generally all that you use. And I was wrong to say that this is the Shannon entropy. The Shannon entropy, technically speaking, is when you take the entropy of a random variable. But Shannon worked in binary, so usually you would take a base of 2, so that was why I made that mistake. Just familiarity. But yeah, that's called bits. And usually people use nats when they're talking about the topological entropy for a function. So usually you'll just use the natural logarithm. All right, that is it. So now you know how to compute the Kneading matrix for any piecewise continuous function on a compact set like 0 to 1 in reals, and to compute the Kneading determinant from that matrix, and then to compute the topological entropy from that Kneading determinant. So that concludes the video. Thank you.